Okay, good work, everyone, and it's really nice to see all these comments. What I would like is to ask for you for some participation of you. So please, if you let's just start with the first question. If there is someone who would like to give the answer to the first question, then please do so. Don't hesitate.
All right, so we have a relation between the absorption cross-section and the, you see, I'm still not 100% on what every symbol is called.
Okay, so Q is the efficiency.
Yeah.
I have no idea why that symbol was chosen, but that's how it is. Sigma is the absorption cross-section, and mu is the absorption coefficient.
Okay, so the absorption cross-section and the absorption coefficient are related by the absorption cross-section is the absorption coefficient divided by the particle density.
Yep.
And then the absorption efficiency is related to the absorbed power divided by the initial power, with the absorbed power being for a homogeneous solution being a multiplication of the absorption cross-section with the number of particles and the incident intensity.
Yeah. That's exactly correct. So I actually liked the efficiency a lot, because that is really a physical thing. It's the absorbed power, how much power is absorbed divided by how much power you put in. So that is just an easy to understand number. The only thing is that it's a little bit challenging to interpret it, whether you interpret it for a molecule or for a particle or for a chunk of tissue. So that makes it a little bit difficult. The cross.
Yeah.
Yeah. Go ahead.
Question: How would you actually compute the efficiency for tissue, since you have like a lot of different particles in tissue?
Yeah. So basically, it is essentially it is just the sum of all the individual efficiencies of the different constituents in the right proportion, of course. But it's really hard to measure. So what if you could hypothetically measure how much how much power you put in, that is usually easy to measure, but how much light is actually absorbed is a little bit more difficult to measure. But let's say you hypothetically could do that, then it would just be the ratio of these two numbers. But the problem, of course, is what we saw, that it so you can calculate this absorption efficiency for a molecule. That is doable. But if you then take a bunch of these molecules in a solution, then it scales linearly. That is okay. But if you put them in particles, then already you have to make some adjustments. And if you put these particles then again in let's say vessels in the tissue, then you have to make even more adjustments. So it is in that sense, it is the definition is pretty straightforward, but the interpretation depends on what scale you're looking at. But that already touches on the second question. What is absorption flattening? And I'm sorry, I just realized that I used the term pigment packing in the maybe not absorption flattening so much in the previous presentation. But that is what I meant. Can someone explain what is this process or this effect of absorption flattening, pigment packing?
Yeah, so for me, pigment packing is clear, I think. I only do not really understand whether it's the same as absorption flattening.
It is the same. It is two terms that are used interchangeably.
Okay.
So if you can explain the process, I would be.
Yeah. So what I thought it meant is that in the last lecture we had the example of I don't know, some sort of aquarium where we had particles, and then they were either homogeneously spread, or they were all on the left side, right side, front, or the back. And then we saw that if they are all on one side of the tank, that the absorption coefficient was then lower than when it was homogeneously spread. And I guess that's because when they are homogeneously spread, you have more tiny particles, but they are in more locations throughout space, so the light has a higher chance to counter one of these particles. I think this is what I thought it was.
Yeah, well, I guess. Yeah, I guess. So what we just to be a little bit precise, we in the example in class we talked not about particles in the cuvette, but about molecules in the cuvette. But you are right in the sense that if I would do the same thought experiment, but now with particles, we would get exactly the same result. So in that sense, your answer was perfect. And yeah, it is also so. If you have molecules that are randomly distributed, then and if we can. Okay, brief sidestep. We have basically two ways of looking at the interaction of light with tissue from a physical point of view. We can think of electromagnetic waves that travel through a medium and that get attenuated or redirected or whatever. Or we can think of the light as photons, really as particles that hit another particle, that hit a molecule or not. And if they hit an absorbing molecule, then this photon. Sometimes I even use the analogy of knickers of marbles. Then it can be annihilated, or it can change direction. So if you now for a moment adopt the picture of photons as photons as particles that can hit another particle and then something happens. If you have these absorbing molecules inside a cuvette, then there is some probability of a photon hitting a particle. If you move all the absorbing molecules to the front of the cuvette, so the part that is facing where the light comes in, then the probability of hitting such a particle for that marble increases a little bit in the first half of the cuvette, but in the second half, because there are no absorbers anymore there, the probability becomes zero. So the photons will pass through that without anything happening. And the effect of that was in net that you would get the same result as if they were distributed homogeneously. If you put them to the side of the cuvette, so again relative to the direction of the incoming beam, then half of the photons will have an increased probability of hitting an absorber, getting absorbed, and the other half will have zero probability of hitting an absorber because there aren't any there anymore. We moved them all to the side. So that part of the light will just pass undisturbed. So you can then write an expression for these situations and see what comes out at the other side, and then you will find that there is a difference between these two situations. So that basically means that tells us that you can have the same amount of absorbing molecules in a measurement situation, but it depends on how they are organized, what kind of absorption you will measure, and then what you will measure is the only thing. So if you want to know the absorption coefficient, the only thing you can do is use the measurement and try to translate that back using a model to the absorption coefficient. That's why I always say the absorption coefficient appears lower, because there's exactly the same amount of molecules in the experiment. If you have them in solution, you will measure a certain absorption coefficient. If you have them in suspension, you will measure another absorption coefficient. And just how that organization is determines how that works. Determines how that what answer you will get. A very so there again, if we try to make a really physical picture out of this, again, if you have a number of molecules that are homogeneous and distributed as a baseline, and then all of a sudden you're going to trap them into particles. That means that there is a higher probability of hitting such a molecule when a photon passes through that particle, but there is, on the other hand, there is zero probability of hitting one of these molecules if the photon passes along the particle. And that balance, that is what the formulas do. That is what the derivation does. Tells us what absorption coefficient we will measure. And then on a larger scale, so that is for molecules and particles, and then on a larger scale, you can do the same thing for particles being either in, or make it even more concrete, for red blood cells, for example, being inside vessels or homogeneously distributed in a piece of tissue. So then so that effect is always there, and if you it's a little bit of a lame argument, but if you look at the formulas, you can see that this effect gets stronger if the absorption coefficient of the molecules is stronger. So so can anyone tell me which situation will give me a higher apparent absorption coefficient if I have the molecules in a suspension or in a solution?
That would be the solution, then, right? Because in the solution, the molecules are free to move.
Yeah. So then, yeah, in the solution, the absorption coefficient that you will measure will be higher compared to the absorption coefficient that you would measure when the particles are in a suspension. So again, let's think of blood. So hemoglobin is the absorbing substance in blood. But now instead of having it free floating in a cuvette, we have it contained in red blood cells. So that means that if we would measure on red blood cells, we would find a lower absorption coefficient compared to a measurement with the same amount of molecules, but then free floating in a cuvette. And the formula tells us that this lowering will be stronger when the absorption coefficient of the hemoglobin is higher. So if we take an hemoglobin solution that and look at the absorption peaks, we see one at 450, for example. There, the effect of this organization will be higher than at an absorption than at a wavelength where the absorption coefficient is a little bit lower. So if you would do the calculation for every wavelength, and that we'll get to that in a moment, you'll see that the really high absorption peaks in hemoglobin are actually a little bit flattened down compared to wavelengths where the absorption coefficient is not that high. So that's where the term absorption flattening comes from. We'll do a little bit more on this, but for now, I just if it's okay with you guys, I want to continue now with the other 3 questions, and then we'll get back to this topic again. Is that okay? So can anyone tell me what the relation is between the electric field and intensity? Or maybe you should ask the question a little bit differently. I've posted a short video on Maxwell's equations. I'm always a little bit unsure if this is. I guess you've seen this once, but I'm not always entirely sure if this is really in your system. So question 1 is, did you actually watch it? And question 2 is, what is the relation between electric field and intensity?
Well, we know, yeah, I've watched it, the video. So we know that for an electromagnetic field, you have the electric and the magnetic field. These two are perpendicular to each other. One goes in the Z axis, the other one goes into y-axis. So the vectorial product of these is the pointing vector, if I'm remembering correctly.
Yeah.
Okay. So we also know that E and B are proportional. They're more likely the same in terms of amplitude. So we know that the intensity is proportional, directly proportional to the squared intensity of the squared amplitude of the electric field.
Yep.
We could also say that it's proportional to the product between the electric field and its complex conjugate.
Yeah, that's because if you have if you write the electric field as a complex quantity, so the idea you know the electric field and the magnetic field as well, of course, can be it has a magnitude and a phase. So it is an oscillating signal which has a certain amplitude and because in time it has a certain phase, and therefore you can write it as a sum of sines and cosines, but you can also write it as a sum of complex numbers. So with an with an amplitude and a phase. And if you want to square a complex number, which is indeed what we have to do because this to calculate this pointing vector, then the proper way to do that is to take the complex quantity and multiply it with its complex conjugate if you want to know the resulting amplitude. So that is what happens. And the good thing of that is that the phase terms in general drop out, so that you can already usually make a shortcut and only look at the amplitude. Do you know the units of intensity? So the physical units. Oh, that's the next question.
Yeah, it's watt over square meter.
Yeah. So it is actually the amount of power that is incident on a certain area. And we'll see that. So there are a couple of different quantities that actually measure that. We in the previous class when I talked about how much light is absorbed inside a tissue, we had this quantity called fluence rate that had the same units. So basically, that just describes the same thing: the amount of power that is going through a given area, a flux, so to say. Okay, then the next question. So the last bullet point question: if we have a purely absorbing medium with a given absorption coefficient, how does the so if you would sketch then the fraction of light after this laser beam propagates through a certain length L, how does that fraction of light look like as a function of L? Anyone?
Yeah, so that's the Lambert-Beers law, which was discussed in the previous lecture. And it states that the intensity as a function of length is the incident intensity times an exponential minus the absorption coefficient times the length.
Yeah.
So what you get for the intensity is a negative exponential or an exponential decay as a function of length.
Yeah, exactly, an exponentially decaying function, and we derived that. There's actually quite a number of ways you can derive Lambert-Beers law, and I'll try to do as much as possible in the coming classes. But the last time we derived it by chopping up the cuvette in very small segments and then calculating how much light actually survived going through that through these segments, and then you ended up with a differential equation, and the solution for that was indeed Lambert-Beers law. Then the last bullet point, which is a little bit of a trivial question, if you know that it has this exponential form. So what fraction of that light is left after you travel a distance? A certain distance that is given by 1 over the absorption coefficient. So the absorption coefficient has units, let's say, per millimeter. So 1 over the absorption coefficient has a distance meters or millimeters. So this actually represents a length.
Yeah, so that's just the incident intensity divided by Euler's number.
Almost. Yeah, so it's 1 over e. It's e to the 1 over e. Right, for Lemke-Beer's law is exponential law. If you mu a times L, if L is 1 over mu a, then it becomes exponential -1. So that is 0.37, I think. Yeah, so that's 37%. What we'll see later. So this property, and that is the reason for asking this question, because I want to tell you that this length also has a name. It is called the mean free path length. As we will see, this is the mean length of that photons travel before they get absorbed. And we'll also see later on that you can do the same thing for scattering. So one over the scattering coefficient is going to be the mean length that photons travel before they get scattered. All right. That is the same question. I'm sorry. I have a few other questions, but I think it's time for a break as well. So let's take a break, and I'm going to leave these questions up here because I would like you to. This is going back to the absorption flattening. I would like you to try these very concrete examples, and let's so take a break and work on it. Let's try to reconvene at 2:45. Is that okay? If you need longer, we'll find out. I'm going to briefly switch off the camera if that's okay with you.